Okay, here, chapter 9, infinite sequences and infinite series. In this chapter, we deal with the infinite sequence and infinite series. The limit law for functions and other interesting properties can be adapted for convergent sequence. The limit of the new sequence essentially defines the sum of all terms of the given sequence, and it is called the sum of the infinite series. Okay, so the sum of infinite series. Infinite series has a wide range of applications. We're going to see what it is. Section 9.1 is an introduction of sequence and series. We know the sequence is a function whose domain is a set of positive integers, and if f of n is a n, then the sequence can be written in this way, or simply in this way, or as the list of the numbers like this, etc. The range of function f are called the terms of the sequence. The a1 is called the first term of the sequence, a2 is the second term, and so on. Okay, here's an example of a sequence. Suppose in this case, a1, an is an minus 1 over n, or this can be written in this way, or, and another example is a sequence sine n pi over 3 from n is equal to 0 to infinity. So the sequence may not be started from 1. So in this case, this sequence starts from n is equal to 0. So there are a variety of choices of sequences. For example, if an is equal to square root of n plus 1, then the sequence can be written in this way. The Fibonacci sequence can be defined in this way, which is popular. It's the addition of the previous two terms that makes a sequence such as this, which has lots of applications. Okay. And decimal expansions. Decimal expansion of a real number is representation with base 10. For example, the decimal expansion of pi is 3.1.159, like this. And this decimal expansion of a real number can be found in Sage command like this. If we go here, and the Sage says that I have developed, then if we make a copy of this, then we may see what first this. Okay, the 17 over 6 can be written as this in a decimal point, and pi can be found in this way, or exponential number e can be found in this way. So those are, so you will use those commands in the Sage for any servers, any servers that has Sage, then you can use this command. And the following table summarizes the decimal expansions of the first few unit functions. For example, there are 1 over 2 has a decimal expansion as 0.5, 1 over 9 as 0.11111 like this. So if we try it, 1 over 9 here, then we will have like this, okay? So 1 over 19, then we have 1 over 19. Then we can have, there is a circulation of the series of numbers. In that case, yeah, we write in this way. Okay, with those information, so at least, yeah, you can list up the numbers in the decimal form to compare with the others. Now we start the limit of a sequence. A real number L is said to be the limit of a sequence, AN, which can be written in this way, as n goes to infinity. If the term AN can be made as close to L as possible by taking n to be sufficiently large. Okay? So this is a verbal expression, and this is a mathematical expression of the limit of a given sequence. Okay, n goes to infinity. So, if a sequence has a limit, then the limit of an plus 1 must be same as limit of nth term of an, s of n, like this. If n goes to infinity, then if the nth term slowly approaches to the L, yeah, then that shows. And this is also shown. So these are the example of 4 sequences that converge to L. We say the sequence AN has the limit L, and we write limit AN is equal to L when n goes to infinity. Alternatively, if for any given epsilon, which is positive, there is a corresponding integer n such that absolute value of an minus L is less than epsilon whenever n is bigger than or equal to n. Okay, that's the pure mathematical expression of this notation. Okay, if limit an exists, then we say the sequence converges. Otherwise, the sequence is called diverse or divergent. This definition can also be stated as follows. This limit an is equal to L means that whatever interval L minus epsilon to L plus epsilon is taken with a positive number epsilon, all the terms of sequence except possibly the first n minus 1, depending on epsilon, lie within the interval. The sequence an is to be diverse, and we write limit an is equal to infinity. If for any given positive integer m, there is an integer n depending on m such that an is bigger than m whenever n is bigger than or equal to n. This is the mathematical expression of this notation. If for any given positive number m, there is an integer n depending on m such that am is minus m instead. So if an goes to minus infinity, which means for arbitrarily chosen interval, then we can always find the big number m such that an is less than minus m. So it's minus m is a very small number, and nth term is even smaller than these small numbers. Whenever n is bigger than or equal to n. So we write limit n is equal to minus infinity in this case. So I will show you, what it really means. Archimedean property says given any real number x, there exists a natural number nx such that nx is bigger than x. 이게 무슨 말인지 이해돼요? Okay, that's Archimedean property. First example shows that asks us to prove that limit 1 over n is equal to 0 when n goes to infinity. So the proof says for a given epsilon, we have to find a positive integer n that makes for every small n which is bigger than or equal to capital N that satisfies this. So we need to find n. So we need to do some side calculation. Actually, this is a side calculation. So we are looking for n that satisfies this one. So what that means is if we change this n and epsilon, that means if n is bigger than larger than 1 over epsilon, then always 1 over n is less than epsilon. So with this information, which can be easily obtained by the side calculation like this. So if we choose this n, this capital N be any integer larger than 1 over epsilon, then for any small n which is bigger than n, which is larger than 1 over epsilon, that satisfies 1 over epsilon is less than, and 1 over n is less than epsilon, which satisfies this one. So that meets the definition of the limit as desired. Yeah. So yeah, for a given epsilon, all we have to do is just find the n that satisfies if n is bigger than or equal to n, then that satisfies this condition, as we have seen. And the next example shows asked us to prove the limit of this is 2 over 3. And so, samely, for a given epsilon, we choose n. So, in order to find it, we do the side calculation like this. So, this minus 2 over 3 absolute value can be written as absolute value of 5 over 3n. So, how we have to choose the capital N from here? So, we just change this n and epsilon like this. So, if this satisfies, we can easily find this relationship. So, we choose the capital N be any integer larger than 5 over 3 epsilon like this. Then we have 5 over 3 epsilon is always less than epsilon if n is greater than n, as desired. 무슨 말이에요? So, it's been proved. For example 3, if absolute value of r is less than 1, then limit r to the n is equal to 0. We have to show that. Similarly, for arbitrarily given epsilon, positive epsilon, we have to determine n. So, side calculation, we need a side calculation. So, Rn minus 0, absolute value. So, we want to find the capital N that satisfies this condition. So, since absolute value of R is less than 1, so, absolute value, so we can easily find a small positive number S that is equal to this. So, here, we use by the binomial theorem, we have chosen positive S that makes the two terms same. Then by the binomial theorem, we can find the inequalities of this. 1 plus S to the n is greater than n times S. So the absolute value of R to the n is less than equal to 1 over ns. So if we choose the n which is bigger than 1 over epsilon s, then we can find these inequalities. So all we have to do is choose a capital N as a any integer larger than 1 over epsilon of s, then if we choose the little n which is greater than or equal to capital N, then always this Rn, R to the n minus 0 is less than epsilon. So this completes the proof of the limit. So this is another example of it. And similarly, yeah, we can do on the divergence. Okay. So the next one is for the divergence. Prove that if absolute value of R is greater than 1, then limit R to the n is infinity as when n goes to infinity. Here, here the method is like this. Choose the positive number, positive number capital M, and then we have to determine the capital N such that R to the n is bigger than M for every n which is bigger than or equal to n. Okay. Anyway, for M, yeah, we need to determine capital N. Since for arbitrarily large capital M, so we first find a positive S that makes R is equal to 1 plus S because R is greater than 1. Then we take the nth power of 1 plus S and then use the binomial theorem to get this inequality. From here, R, which is 1 plus n, then nth power of both sides can be less than n times s. So if we choose n greater than m over s, then it makes ns is bigger than m. So if we choose capital N be any integer larger than m over s, and we choose little n bigger than or equal to capital N, then it always makes R to the n is bigger than m, capital M. That this completes the proof. And the following theorem immediately follows from example 2 and 3. So, if we summarize, the following theorem follows from the above examples. Limit of geometric sequence. So if R is in between here, then this sequence converges. But for any other values of R, the sequence diverges. So we can write in this way, which can be shown in figure 2. So for the value R which is bigger than 1, it always diverges. For any value which is for any value of R which is less than or equal to minus 1, it diverges. But it converges when R is in between minus 1 to 1 and R is equal to 1. Okay, and those are what you already know. And you know, you know what's the limit of AN is equal to N means. And the limit law for sequences is, you know this limit the laws for sequence, limit laws for sequence. You have seen it for many years already. So I'm gonna just mention that. And Ski's theorem, or the sandwich properties, is this: if AN and BN CN has this, that satisfies these inequalities for all n which is bigger than a certain fixed n naught. And the limit of AN and limit of CN is equal to a finite number. then the limit of the middle terms, the sequence, should be same as L. So this is the Bn is in between those two, so it's called sandwich or squeeze. And if this goes to L and this goes to L, then the middle one should go the same limit. That's what it says. It will be referred later as a squeeze theorem or sandwich property. Another useful result is the application of the squeeze theorem for sequence, like this. If limit a absolute value of an is equal to 0, then limit of an should be 0, because the absolute, the an is in minus an is in between and plus an. They all goes to 0, so the middle term an should goes to 0. The other one is this. Find the limit of n of 1 over n when n goes to infinity. And you just divide it by n on both sides of numerator and denominator. Then we have this term. Then if n goes to infinity, then this goes to 0, so it goes to 1. So it converts. All those can be done by the limit laws that we have introduced. Find the limit of this one. In this case, we could not use the L'Hopital's rule because this is not a continuous function. But if we think the related differential function like this, instead of the n, if we think as a function x, then we can apply L'Hopital's rules to find the limit. So for the function f of x like this, then when x goes to infinity, L'Hopital's rule was applied to have the derivatives of the both terms, and then x can be this can be written as 1 over 2x squared. When x goes to infinity, this goes to 0. So consequently, we can say the limit ln of n over n squared goes to 0 when n goes to infinity. So there are several techniques that we can use. But the sequence minus 1 to the nth power diverges because it oscillates. Okay, yeah. This example 8 is one example of the squeeze theorem that we just mentioned. Since the absolute value of the terms limit the converts to 0 as n goes to infinity, the original terms also converge to the same number by the squeeze theorem. Next one is the criterion for convergence of monotonic sequence. We say that a sequence an is strictly increasing if the an is always smaller than an plus 1 for all n greater than or equal to 1. And the sequence is strictly decreasing if an is always greater than an plus 1 for all n. And sequence an is called monotonic if it is either increasing or decreasing. This will be it will give us one very interesting and important theorem. Okay, now we start from example 9, which asks to prove the sequence an is decreasing. Let's see this term. Then we can easily show these inequalities for the term nth term and n plus 1th term. Let's see how we can do it. An plus 1 minus an can be written in this way. So this term can be written in this way, which can be simplified in this way. But as you see, this is always positive for all n is greater than equal to 1. So we can, since it has a negative sign here, so an plus 1 minus n is always negative, which means for all n, we have the inequalities in this order, which means it is decreasing. Not only decreasing, it is strictly decreasing. Okay. Okay, next. But there is another way of showing it. Let a and be a function of n, like this, like f of n. Then f of x can be written in this way. Then f prime of x, we can show f prime of x is always negative, because this is a square and this is positive. So if you multiply -5, it is always negative for all x which is positive, like this. So we can say, we can determine that f of x is decreasing on interval from 1 to infinity, which tells us that the sequence is decreasing too. So there are several ways of showing whether a sequence is decreasing or increasing. A sequence is called bounded if there exists a positive number m that satisfies this for every n. This is the important theorem. Any convergent sequence is bounded. So if a sequence is unbounded, then it is always divergent. Okay. We can use the definition of limit to show this simple fact. The next thing. This monotone sequence theorem is one of the most the important theorem that we're going to use a lot. Every bounded and monotonic sequence is convergent. If a function, if a sequence is monotonically increasing or monotonically decreasing and bounded, then this sequence is always convergent, like this. So, bounded and monotone, then it is a convergent sequence. So in this case, so if we use this theorem, we can save a lot of time to check whether a given sequence is convergent or divergent. Okay, and this is another interesting example that determine whether a sequence AN defined by the recurrence relation, like this, is convergent or divergent. 자, okay, as you see, this term is increasing and to the direction, to the number 2. Okay, so we may try to find the limit of it. Okay, so sequence AN and this term seems to be increasing and approach it to 2. So we use a mathematical induction. The starting point is assume true for n is equal to, show true for n is equal to 1. It's true because A2 is always bigger than A1. Okay, because we are adding some number over the scale root 2. So assuming that it is true for n is equal to k, then we have to show it is true for k plus 1. Okay. Okay. So yeah, from the assumption, from here we can draw this fact, which implies an plus 1 is bigger than an. Which means it is true for n is equal to k plus 1. So we have found it is monotonically increasing. Monotonically increasing. We have shown that. Then next, we show this sequence is bounded. Also, we use induction. So an is a1 is less than 2, so it is bounded. We proved it is true for n is equal to 1. So assume true for n is equal to k, which means k plus 2 is bounded. And also since we want to verify an is less than or equal to 2, so we showed it. It is true for n is equal to 1, that it says a1 is less than equal to 2, less than 2. So we want to show, we supposed it is true for n is equal to k, which means ak plus 2 is bigger than 2 plus 2, which is 4. So we assumed this. Then we want to try to show the next term is also satisfy the same conditions. So from the induction hypothesis, we have assumed the ak is less than 2, so ak plus 2 is less than 4, which means ak plus 1, which is square root of ak plus 2, is less than square root 4, which is 2, which means is satisfied for the case n is equal to k plus 1. So by the mass induction, we can say it's always the nth term is less than 2. So all the terms are less than 2, which means it is bounded, the sequence. So this series is monotone and bounded. So by the monotone sequence theorem, it converges. That's what it says. If it converges, then there exists a limit L. And L should be same as square root of 2 plus L. Because this is an nth term, this is n plus 1th term. So the limit should be same. So at the end, the two limits should be same. Limit of ak and limit of ak plus 1 are same when k goes to infinity. So this L should satisfy L is equal to square root of 2 plus L. If you solve it, then L should be 2 or minus 1. But L must be positive, so L should be 2. So the limit is 2. Okay, next. Determine whether the sequence n converges or diverges. If it converges, find the limit. So how are you going to find the limit of this? So you may approach this by dividing n square on both sides of numerator and denominator to get the minus 2 over 5 as a limit. Okay, I may check your answers in here. So if we see it, then this shows what? This shows it goes, the terms goes to, as n goes to infinity, it converges to the certain point like this. So you can easily draw the graph by giving this command. We had the function like this, and we draw the function, and also we pointed out the point when n is equal to 1, 2, 3, 4, 5, 6, like this. So we see this converges to where? Minus 2 over 5, like this. So we can verify. You can verify what do you have in here. So and also if we copy this and give a command here, then it gives us the limit like this. If we change the function, maybe 1 or here 5 or whatever, and giving anything, then we can also find the variable goes to infinity. Do we use the n, limit n goes to infinity? Any? Okay, so if we define a variable n and then find the limit of any function that we make change, then this function, this command gives us the limit that we are looking for. If we change it to like this, then it will give us the limit of these different functions. So now you can solve the problems which is given in the exercise of this section. Next part is a series. Now you have dealt with the sequence, and then we think series. Given a sequence, we use a symbol like this. This is a summation of each terms. And this symbol is called the infinite series, or just a series. Then we can also think of a new sequence, Sn, where S1 is a partial sum of first one, S2 is a partial sum of first two terms, S3 is a sum of three terms, first three terms, like this. Then this is another sequence from the partial sums. This number Sn is called the partial sum of the series, An, summation of An. If this sequence Sn converges to S, then we say that the series summation An converges, and write the summation of An from n is equal to 1 to infinity is equal to S. The number S is called the sum of the series. In other words, we can write in this way. Summation from 1 to n, and send the n goes to infinity. Then this is the same notations. If Sn diverges, then series is also diverse. For example, 1, 2, 3, this series has a partial sum like 1, 3, 6, 10, 15, 21, and after nth term, it's getting bigger and bigger, which becomes very large and has an increase. So this series diverges. On the other hand, this series, the series has a partial sums like this, 1 over 2, 3 over 4, 7 over 8, like this. Then which converges to 1, because this goes to 0. So the series converges, and its sum is eventually this, which is 1. So there are many diversity of the series. Let A and B and be two sequences such that An is equal to Bn plus 1 minus Bn for all n greater than or equal to 1. Then this case, summation An is called the telescoping series. Telescoping series has many interesting properties like this telescoping series, and there are lots of information and which is already discovered on this special case of series. What it is this, and this some technique can be applied for this special type of series. Such a technique is also known as the method of difference. Here, this example shows the method of difference. Show that the series is convergent and find the sum. So we make this nth term as a difference of two terms like this. Then it turned out to be a telescoping series, and the nth partial sum can be written in this way. In this case, the middle terms can be cancelled like this, isn't it? So eventually we have only two terms. Then limits can be easily found. Limit of Sn can be easily found, found because this goes to 0, so we have only 3 over 2 as a limit. Since the limit of Sn does exist, so the series converges, and this value is 3 over 2 like this. So if we can make a term as a difference of two series, that makes the calculation much easier. Another simple form of series is a geometric series like this. Geometric series. If in this, for the geometric series, when absolute value of r is less than 1, then series converges, and the limit can be found as a over 1 minus r like this. But if absolute value of r is greater than 1, then series diverges. You know how to find it. When r is not equal to 1, then we have Sn can be written in this way. If r is less than, absolute value of r is less than 1, then it goes to 0, so eventually we have the first term like this. If r is greater than or equal to 1, then it diverges, definitely. Because for the case when r is bigger than 1, then Sn is always bigger than n, and if r is less than minus 1, then it diverges. So the limit does not exist. So you know this fact well already. And use those theorem, then we can find the sum of the geometric series like this without much difficulty. Because the first term is 3, and the ratio is minus 2 over 5. So you just use, add 3 here and r here, minus 2 over 5 here to get the limit, 15 over 7, something like this. And write the number, this, as a ratio of the integers. How? Okay, so in this case, we can write this number in this form, and then we can figure out this is a geometric sequence with the ratio 1 over 10 square. So this number can be found as a 35.33 plus this, because it's a geometric series. So the answers would be 2933 over 550. We are almost there. The necessary condition for the convergence. If the series converges, then the sequence converges. The series converges, then sequence converges. Because if we write an is equal to Sn minus Sn minus 1, and so actually this is true for all n. So nth term is a partial sum of up to n minus partial sum up to n minus 1 term. The series converges to S, which means the limit of Sn and limit of Ns of n minus 1 is same. So these two are same, which means this limit is equal to 0. That means limit of an is equal to 0. Okay? Okay. And this the figure 5 shows the situations like this. Yeah. If Sn converges, then the difference between those partial sums getting smaller and smaller and approaches to the 0. That's what it says. The An goes to 0. And this is, the difference is getting smaller and smaller, so eventually difference would be 0 like this. Okay, the condition An, but the series may diverge even though the limit An is equal to 0. Here's the example. 1 over n. So in this case, 1 over n does converge to 0, but the series is diverse, as you know. This is called the harmonic series. Here. Yeah, you already knows it very well. Right. And test for the divergence. If limit An does not exist or limit of An is not equal to 0, then the series is always divergent. That's the contrapositive of the previous theorem. Isn't it? 그렇죠? Yeah. And next example shows it verifies this test for the divergence. So the limit of this is this nth term is 3/7, which is not 0. That means this series diverges by the above theorem. Sum of two convergent series like this, then you can take off the constant out of it, and you can separate the series, and you can split like this. And find the sum of the series like of this. Then this is the example that we have seen in example 13. And as you see, the limit of this is 3/2, and limit of this the second term is since it's a geometric series, we can easily find the limit of it as a 1. Then the limit of these two, the difference of the two terms, the series, this series is just 3/2 minus 1, which is 1/2, which can be easily obtained from here. Okay, like copy. And you do play all these in Chrome, then it will work well. Or Firefox, not in the Internet Explorer. As you see, this series and this series, and the difference would be 1/2, like what you see here. 1/2. We found the limit of this one, and we found the limit of this one. We found the limit of two series, and the difference is 1/2, like you see. And the last remark of this section is the convergence or divergence of series is not affected by adding to or subtract it from it a finite number of terms. So for the convergence or divergence of this one does not affect by this finite terms here. It only affected by this. Okay? So if this converges, then this converges. If this diverges, then this diverges. That's it. Similar argument can be applied for the divergence of the series. Okay, this is the statue that I took a couple of years ago. This is John Harvard, who is a founder of the school there. And there's examples here, and you are asked to solve a couple of problems and upload it in Q&A, as I assigned it before. Here in Q&A, I mentioned that some of you are asked to solve a couple of problems each week and each sections. I think that's it. Here, I will give you a chance to deal with these problems. And most of the problem has solutions and also website and QR code here. So all you have to do is just go through it and change the function and to play with it and upload it to make your homework and the presentation later. Okay, I think that's all for the section 9.1. Any questions for section 9.1? This is the old calculator that we used to have. Okay, now. Okay, any questions?